You're like,
All right, the next part we're going to. Are we?
sorry, my bad.
Okay, so the next part we're going to talk about it's called the standard enthalpy of formation. So you will see this a lot. So just to let you know, what is be aware what is that? Some people call the standard condition of the thermochemistry. Standard condition in thermochemistry. So standard condition. If you're looking at the delta H, we talk about delta H is a change of the enthalpy, right? It's a change of the enthalpy. So could be talk about a change of enthalpy of some certain reactions. So if you're the people, you see there's a subscript for Rxn, then that means this is change of the enthalpy for these reactions. And sometimes they also write delta H and then they write COMB. And this is talking about the enthalpy of combustion, right? This is enthalpy change of combustion. Of a combustion. This is a specific talk about a combustion reaction. And this one just to talk about this is for everything, okay? Doesn't matter what kind of reaction, it's just the enthalpy change of these reactions. But sometimes you will also see there's a there's a small circle. Maybe it's not O, it's just a 0 or it's just circle and Rxn over there. So what does the circle mean? The circle over here is what we call the standard condition. So the circle is a standard condition. The circle is a standard condition. I mean, so what exactly is the standard condition? So if people write delta H, then has a little circle on the top on the superscript. And then the standard condition, they're including two things. One is the temperature. So the temperature of the standard condition have to be in 25 Celsius. That's in thermochemistry. Okay, thermochemistry, let's talk about 25 Celsius or 298 Kelvin. And the pressure is about 1 atmosphere.
So I just want to clarify that
Yes.
there's only heat changes with chemical reactions, right? Like that's not going to happen with the physical.
No, with physical, then we call this process. It's not a chemical reaction because, for example, you have a condensation, you have a melting process. That's a physical change,
Right.
but that's not a
But
chemical
there's not
change.
going to be any heat. Like
There still have a heat exchange.
okay, so this can happen with both chemical and physical reactions, basically.
Yes, but usually we only talk about that. So that's the delta H, remember, it's just a heat exchange.
Right.
So it doesn't matter it's during the chemical reaction or physical process. Okay, yeah, that's just a delta H. But if you write delta H Rxn, then that's a specific talking about the chemical reactions.
Okay,
That makes sense?
that makes sense. Yes, thank you.
Okay. So the small O circle here is talk about standard condition. Why we need a standard condition? That's a good question, right? Why do we need a standard condition? Well, standard condition, that's gonna be I mean, at least if we set up a standard condition, then everyone will be noticed. Okay, this reaction, the value for certain condition is happened in standard condition, not happened in other conditions. Give you one of the examples, right? Give you one of the example. We have Okay, so we combust some of the reactions. Let's say propane. Propane gas is reacted with oxygen, right? It will produce a CO2 plus H water. And then we're going to have a delta H of the reactions. And then that's going to be different for the delta H values, okay? Because the delta H value, the delta H value is really depends on what's the temperature of this reaction happened, or what is the pressure that occurred in these reactions. That makes sense, right? If your work in the room temperature, like a 25 Celsius and 1 atmosphere, so obviously you can only just make a liquid over there. So the delta H, the value will be completely different when the reaction is happened in 150 Celsius and 1 atmosphere. That makes sense, right? Because the state of those the water is different. So the chemical reactions, how much heat you produce, that's going to be also different. I'm not sure whether are you clear or not.
The change in heat is dependent upon the temperature. Is that what
The
you're saying?
heat is
Right.
depends on the temperature.
Okay, cool.
Okay, how much heat? For example, okay, so if the room is really cold, and then generally I'm going to release much more heat. But if the temperature is hot enough, sometimes, I only just need to release a little bit of heat, and then I'm done, I'm okay, right? So this is the same thing. The chemical reactions is doing the same thing. The chemical reactions, how much heat the chemical reactions will produce is really depends on the environment. If the difference, the heat is, it's too cold, they're going to produce quite a lot. Okay, but if they only have, the temperature is high enough, then they probably won't going to produce enough heat. Because you produce more heat, generally it is resistant to the reaction goal. Okay, so generally the temperature. So what I'm talking about here is the delta H of a certain reaction depends on the temperature for your observation. So that's why people would like to make a standard condition. Otherwise, you're talking about the apple, I'm talking about banana, right? It's same reactions. You say, okay, this reaction produce like 300 kilojoule, but I'm only just observe 50 kilojoule. How come? Because they may happen in different conditions. So the people set a standard condition, and then everyone talk about the same condition, and then you can compare how much heat you produce, how much that produce. Does it make sense, right? So this is why the people need a standard condition, okay? And then, since we talk about standard condition, and then we will going to talk about another topic. It's called standard enthalpy of formation.
Basically, what you're getting at is that the true delta H of that equation lies somewhere in the middle of those 2 degrees.
What do you mean? There's no true delta H. And just to let you know, delta H always has a value,
Right,
but that's really depends on what's the temperature.
right, but like for that formula that you put,
Mm-hmm.
if you go up a little bit,
Yeah.
and I went through the circle, like you're saying, the delta H lies in between those 2 different temperatures, or?
No, the delta H, same equation will have the different delta H value
Right,
when your temperature change. So maybe this one, they produce a negative 890 kilojoule. But if you raise the temperature at 150 Celsius, the delta H value will change. So this is standard condition, this is value. Then it will change, maybe become a 500 kilojoule. Okay, so we'll still have a value, but the value will be different from the standard condition.
right.
Just to let you know, this is what happens. Okay, so then you cannot compare you cannot compare those two values because those two values is not happened in the same temperature and not in the same condition. So you cannot compare. The easy way is, okay, I have two reactions, reaction A and reaction B. One is react at 100 Celsius. One react at 10 Celsius. But they all produce 500 kilojoule of heat. And which one is gonna be produced more? Or are those produce equal energy? You cannot compare because those two reactions not happened in the same situation. One is happened in 0 Celsius. One is happened in 100 Celsius. You cannot compare those two, although they produce the same heat. But what if they're at the same condition, like 25 Celsius and 1 atmosphere? Which one will produce more heat? I don't know. You cannot compare those two values. That makes sense? Are you clear now? Kind of. Yeah. So, the purpose of this is just to try to make every scientist in the same page. So then we can compare the numbers, and also we can utilize the numbers. Okay, yeah, so that is why we have a standard condition. All right, so the next part, we're going to talk about the standard enthalpy of formation. Before I talk about this, I will make an analog, because sometimes this one is not that easy to understand. Okay, so first, let's talk about, we have two mountains. Okay, so if we have two mountains, I want to know what is the difference between difference height of those two mountains. Then usually what we do, how do we calculate the difference of the two mountains, the height of two mountains? Your what?
You can add them and subtract it.
You add them and subtract. So generally you try to find the difference. If you know this higher mountain is 1,000 feet, this is like 500 feet. So the difference over here is just 500 feet, right? So this is what you got, right? But I'm just asking, okay, well, then how can we determine, how do you know the feet, the height?
I'm climbing it.
That makes sense.
Just count your steps on it.
How do you got how do you got the 100 feet, 500 feet? You search online?
Yeah.
But where the online numbers coming from?
And someone measured it.
Someone who's smarter than me.
Someone measure it. The satellite can measure it.
So it's
But
not
the point-
everything on Google is
but-
real.
But the point is, okay, mountain, some of the mountain underneath is also very high. Some of the mountain underneath maybe is not that high. I'm just saying, okay, so some of the mountain, okay, it's not that high in the outside, but it's gonna be very high in the bottom parts. How do you measure it? That's gonna be a question. How do you measure it?
If it's underground, it counts. Is that what you're saying?
Sometimes it counts. Okay, so that's why. Okay, you're based on your rule. I based on my rule. So how can I know? What is the absolute value of the mountain?
Sea level.
Great. You see?
Yeah.
So no, so that is why. Okay, so I'm talking about things. Okay, if you want to know, okay, so we need to set a rule. We need to set a rule, and everyone will agree. We're going to base on the height of the mountain above the sea level. So we call sea level is 0, right? We call the sea level is 0. Everything above it is the height of the mountain. So this is the people make the rule. And then we use the rule to find the difference of these reactions. sorry, find the difference of the height, and then we know the difference of those two mountains, right? And standard enthalpy of formation generally also talk about similar thing. Okay, so this is analog. Then let me talk about chemical reactions. So generally, we talk about chemical reactions. The chemical reactions can also be calculated in this way. So for example, I have A plus B to form 2C, and I try to figure out what is the enthalpy of these reactions. And then how can we do this? Well, the good thing is if you know the energy or the heat, if we know the heat, the enthalpy, the heat of the A, and also I know the heat of B. And meanwhile, I know the heat of the C and I times 2, the difference of those two will be just the difference of the heat of the reactions. That makes sense, right? Or another one is the A, if it's the A, if they have like 500 negative 200 kilojoule of the heat. The A containing that much heat. B containing 100 kilojoule of the heat. And the C, if we form C, the C need how much the heat? Maybe a negative 50 kilojoule of the heat. So now the difference of those heat, this one add together is negative 300. And this one add together is 50 times 2, negative 100. So the difference between 300 and negative 100 is how much heat of these reactions. Just like you measure the mountain height, all right, okay? So this one, you measure the difference of the mountain height. You measure the difference. The difference of that actually is just the change of the enthalpy of these reactions. Does that make sense?
Yeah.
Okay, so that's why the delta H of this reaction is usually what we talk about. That's gonna be the enthalpy change of the reaction, the product, subtract the sum. We should say that's gonna be sum of the enthalpy change of the product, subtract the sum of the enthalpy change of the reactant. Okay, reactants and products. Then this is how we figure out the enthalpy of the reactions. So you see the sum of this one is a negative 50 kilojoule and your time 2, because we have a 2 of the C. And you subtract the enthalpy change of this, you have a negative 200 kilojoule. And since this is one of them, so you just keep one of this. And this is also 1B, so that's going to be one of that, plus negative 100 kilojoule of the B.
Oh, never mind.
Because
No, I got
what
it
I
now.
gave you this. So now you have a negative 100 kilojoule, subtract negative 300 kilojoule. And then you can do the calculation. That's going to be a positive 200 kilojoule. In another word, this reaction is actually an endothermic reactions. Okay, and without the energy, this reaction will not go. They have to receive the energy to make these reactions. Yes.
So they need to receive exactly 250 kilojoules of energy to make the reaction go, correct?
Yes. Okay. So then the difference, you see, the difference of the enthalpy for each of this, will be the enthalpy of these reactions. And generally is how we calculate the difference of these reactions. Does
Is
make
it entropy or entropy?
this is the enthalpy, not entropy.
Are those two different things?
Yeah, different things. This is enthalpy. Okay. Entropy we will talk about in the Chem 2 class. Okay, not in Chem 1. So are you clear? This is one. Okay, but remember, I only talk about difference. And there's another one. How do you compare? How do you know that each of the, just like this, when we talk about mountain, how do you know each of the height of a mountain?
From the sea level.
From the sea level.
to the top.
So the people have to define what is the height. Maybe that height is not the absolute value of a mountain, okay? But that is a standard. The people determine, okay, that's gonna be the height of the mountain. Are you clear what I'm talking about? Okay, so that is why the enthalpy actually is the same thing. How do you know? For example, how do you know? How do you know this one is a negative 200? How do you know this is a negative 100? Where this value coming from? What is where they compare? Where they compare to, right? So what they compare is just like we need to compare the sea level. The sea level is 0, and here is also has something as 0. The people assume the enthalpy of a certain, this is what we call the enthalpy of formation. So that's how we put F up here. This is the enthalpy of formation. Enthalpy of formation. So the people define the enthalpy of formation of element at standard condition and in most stable form is 0. Okay, so this is a people compare. So enthalpy of the elements at a standard condition in most stable form is 0. So that's talk about the enthalpy of this. So now you already know what is the standard condition, right? That's gonna be a 25 Celsius and 1 atmosphere. Okay, so for example, like oxygen and O3. So now, if you're talking about oxygen, we have 3 different elements over here, right? O2, that's a very common oxygen diatomic gas, right? This is what we talk about. Then the oxygen could also be an oxygen atom. And also we can have ozone, that's ozone. So those 3 are all elements belong to oxygen. But which one will be the 0? Which means which one will be the enthalpy of formation is 0. Which one?
Diatomic.
Then you need to say, here is another one. It's called in most stable form, which means oxygen is the most stable form. So that's why this guy is diatomic. So that's why this guy, delta H, the formation of the oxygen gas will be equal to 0. But if you're talking about the delta formation of the oxygen gas, oxygen atom is not 0. The ozone gas is not 0. Only this guy is 0. Are you clear?
Because oxygen is diatomic.
Are you clear? So this is by definition in these cases. Okay. Yeah. And the most stable form at 25 Celsius and 1 atmosphere. Then I'm saying, how about enthalpy formation of the oxygen liquid? Is this 0 or not? Then you think about, is that possible? No, right? At 25 Celsius, 1 atmosphere, oxygen is just oxygen gas. They cannot be a liquid. So if you want to form the liquid, you need to give it energy. Yes, this guy need to release the energy to form that, right? So this guy definitely is not 0, okay? at a standard condition and in the most stable form, and that is zero. Okay, so this is how the people compare the zero. How the people compare zero, and then if you're talking about, okay, for the zero, then if you're talking about enthalpy formation of the nitrogen gas, then that's gonna be zero, right? Because that's an N2. Enthalpy formation of a copper solid, well, sure, then that's gonna be zero. But if you're talking about delta H of the copper liquid, then definitely this is not a zero, right? And if you're talking about delta H formation of the chlorine gases, yes, this is also gonna be zero because of chlorine in the 25 Celsius, that is a gas. Okay, and if you're talking about, okay, enthalpy formation of a carbon, well, enthalpy formation of carbon, then that's not be, then you need to say, okay, carbon must be a solid in the room temperature, right? And carbon, there's a different, there's a diamond, and there's a graphite, or some other carbons. Most common stable form, that's just graphite. Okay, yeah. So that's why this guy, the solid graphite, is equal to zero.
So how are we supposed to know all the rules of what state each element needs to be in besides Brinkley-Hall?
Then you just need to make sense. Okay, what is the sense for the metals? What is the room temperature? What is the state for the metal? Most of cases solid, right?
Oh,
Except the mercury.
Okay.
Except the mercury, right? It makes sense, right?
Yeah.
Okay. For the gases, what kind of gases? I mean, we have how many gases do we have? Nitrogen. Those are elements, remember.
There's a brief.
Nitrogen is a gas, oxygen is a gas, fluorine is a gas, chlorine is a gas. And silicon, what do you think? Solids, right? Phosphor, solids, sulfur, solids, chlorine is a gas, right? Arsenic is solids, selenium is solids, bromine is a liquid. This is a solids. So most of the cases, those are all solids. Only just several gas, right? N2, O2, F2, Cl2. Only those four are gases.
And H2.
And the hydrogen, H2, right? And you're talking about the bromine is a liquid.
Wait, iodine isn't,
Iodine is a solid.
but isn't it diatomic?
It's a diatomic. All of those F, all this F, the 7 group are all diatomic.
Yeah, it's gonna.
So there's a Cl2, F2, Br2, I2, O2,
solid,
and
liquid,
2.
gas.
Okay.
gas.
Yeah. So you see, for the gas 1, 2, 3, 4, and 5 over there, right? And here you see the green color are all gases. The green color are all gases. But usually we rarely talk about those the noble gases, right?
But the blue ones are liquids.
Blue one is a liquid. You see, it's already marked over there.
I'm missing.
Interesting.
So you see that is this is a standard. Why this is a standard? Okay. Yeah. Then
But carbon is the only one that's red.
now we talk about, okay, those elements are zero. And then let's talk about how the carbon or how the compounds. How can we figure out the enthalpy formation of the compound, right? We talk about those elements are zero, but how can we figure out the enthalpy formation of those elements, those compounds? For example, let's talk about water. So water can also has enthalpy formation, and let's just talk about the liquid water. Okay, water can also has the enthalpy of formation. So remember, what is the formation mean? Form something. Formation here is try to form this. Well, in other words, try to produce this. So enthalpy formation is talk about how much energy that to form this water, right? If we talk about enthalpy formation of water, it's talk about how much energy that you are going to produce to form water. And form how many water? 1 mole of the water. So that is enthalpy of formation. So in another word, the enthalpy formation, so we are going to form 1 mole of water liquid, 1 mole of this. And then where this coming from? It's coming from their elements, and also is the most stable form elements. So they have a hydrogen and oxygen. Obviously, they coming from hydrogen gases and also oxygen gases. Enthalpy formation. And then you can balance these equations. Since we're only going to make 1 mole of water, so the equation will be just stick with 1 mole of water over here. So 1 mole of water, you're gonna have a 1 coefficient on hydrogen and 1/2 on the coefficient on the oxygen. So you see, this is the equation that associated with enthalpy formation. And you can think about it. So delta H, so the enthalpy of this reaction should be equal to what? Remember, we just talked about that should be equal to the how much energy for the water, right? How much energy, the enthalpy of water, subtract the sum of the enthalpy of water and hydrogen. So enthalpy of the hydrogen plus 1/2 of the enthalpy of the oxygen, right? We just talked about this. The enthalpy of this reaction should be equal to this minus this, right? We just talked about that's going to be the difference. So product minus the reactant. Okay, how much of the energy for the product, subtract how much energy of the reactant. And then remember, we just mentioned enthalpy formation for that one should be equal to what? Enthalpy formation of this one, that's a 0. That's a 0, right? Boom, that's great. So then you will figure out actually the enthalpy of this reaction will be just the enthalpy of formation of the water, liquid. Well, you may confused. Okay, why I'm talking about this? This one, I just let you know, this reaction, how much the heat that produced by these reactions to form 1 mole of water, how much heat is produced, the enthalpy of this reaction will be equal to the enthalpy of formation of water. Okay, because the hydrogen, oxygen, those are all zeros. So the enthalpy formation of here is the enthalpy of the reactions. Well, the good thing is in the lab, you can do this experiment, and then when you do the experiment, you can figure out measure the heat. Then you will figure out the enthalpy of formation. This is also where the scientists start to collecting the data. They start to working on those simple reactions, and then collect the enthalpy formation of those reactants, of those products, and then they can record the numbers. Then later they can use the enthalpy formation of water to the other reactions. Okay, yeah. So here, I think I talk a little bit more of this. So I'm going to just call back what we're gonna do for this one. You just remember, okay, what is the enthalpy formation? Which one is 0? Remember, enthalpy formation of what is 0?
There are diatomic elements, there are metals.
Elements at 25 Celsius, 1 atmosphere, and also they are the most stable form. Those guys are 0. Right? So this is by definition. Second one is the enthalpy of the reaction should be the sum of enthalpy formation of the product subtract the sum of enthalpy formation of the reactant. So this is the second part we talk about, right? This is the This is the parts. And the last one is how to write the enthalpy formation of something, right? We talk about for water, enthalpy formation. If we want to write an equation associated with enthalpy formation of water, of the liquid, then that's just they're going to form 1 mole of water liquid. And then the reactant have to be the elements and the most stable form. So oxygen gases, hydrogen gases, and then you balance this equation. So this is 1 and this is 1/2. So the enthalpy of these reactions will be just equal to the enthalpy formation of the water liquid. And if we talk about something else, okay, if we want to figure out the enthalpy formation of the nitrogen, is NO2 gases, then again, we're going to form, the reaction should be we form the 1 mole of the NO2 gases, one more of this NO2 gas, and then they are coming from the elements of those 2 elements where they form this compound. Okay, and those 2 elements have to be formed in a most stable form, which is this is NO2 gas, and this is a O2 gas, and this is gas, and this is also a gas. And then you just balance this equation, then that's it. This is a 1/2 of the nitrogen, and this is a 1 oxygen. So enthalpy of these reactions actually is just equal to the enthalpy formation of the NO2 gases. So in general, if you're looking at here, enthalpy formation, the equation always is forming 1 mole of the gases.
So therefore, the entropy of the reaction will be the entropy of the formation.
Enthalpy of formation of the
Will
certain
be.
compound. Remember,
Right, so whatever the reactant is, or I'm sorry, whatever the product ends up being.
yeah,
Actually, typically the formation, standard entropy of the formation of the product is going to be the standard
yes.
entropy of the
Yeah,
reaction.
yeah, based on this equation, based on these equations. Okay, so I give you one of the examples. I can give you some of the examples about the enthalpy formation.
And this is one.
You see, this is generally those are the enthalpy formation of the certain compound. Let's see. Okay, so those are silver is a 0, silver chloride, they have a number for the enthalpy formation. Aluminum solids is 0, aluminum oxide, they're gonna have a number of formation. Bromine gas is liquid, bromine liquid is a 0, and HBr, they have a numbers. And I'm just showing you where this number coming from. I mean, so you're gonna have a number come from. I mean, where this number coming from? Coming from these equations, the sum of the chemical reactions. The people want to figure out the enthalpy formation. We got a number. Where this number coming from? They're coming from, we're formed using 1 mole of hydrogen reacted with 1/2 mole of oxygen, and then we combust this reaction, and we can absorb. We can calculate how much heat that produced from these reactions. Then we can figure out, okay, what is the enthalpy formation of these reactions? Okay, so generally, I'm just trying to telling you where this number coming from. This number is coming from the chemical reactions. And this reaction is what we call the enthalpy of formation of the reaction. Okay. Okay, so maybe I talk too much, but here, the majorly how we use the enthalpy formation is just to try to figure out the enthalpy formation based on the chemical reactions. Try to figure out what is the chemical reactions based on the enthalpy formation of the reactants. I know this is always is the hardest part. So take out your study guides, and then let's work on some of the questions. Okay, so let's work on the first question in the page. This is in the page 12. This is let's work on the question in the page 12. Okay, so to understand this, sometimes it's hard. I totally understand because this is the physical chemistry part. But it doesn't mind to using those concepts to solve the problem. Okay. For example, we try to figure out the enthalpy of these reactions. We have 1 mole of methane react with 1 mole of the chlorine, and we're going to form CH2Cl2 and 2 moles of the HCl. And we try to figure out, okay, what is the enthalpy of these reactions? Then how do we do it? Well, we already mentioned that. To find this enthalpy of this reaction, in general, is just using the sum of the enthalpy of formation of the product, subtract the sum of the enthalpy formation of the reactant. So that's it. Okay, and then what do you need to do? You just need to find, okay, what is the sum? Which one is enthalpy formation that belong to the product? And which one is enthalpy formation that belong to the product? And then you add them together and then make the difference. Then that's it. This one is not hard, right? Okay, so now, okay, so this is the product CH2Cl2 is product. So this guy is product negative 95.4. Okay, and we have 2 of the HCl, you plus 2 times HCl. HCl is negative 92.3, negative 92.3 kilojoule per mole. And now the sum of here, this number, you add them together, that's going to be the sum of enthalpy formation of the product, right? Remember, I just try to figure out the difference between those two, because the difference, that's going to be the enthalpy of the reactions. That's it. Okay, that difference will be the enthalpy of the reactions. So this is the sum of the product. Remember, we only just got a product. Then you're gonna subtract the sum of the reactant. The reactant one, if we have 1 mole of the methane, which is negative 74.6, that's kilojoule per mole, and we got methane. The next one is chlorine gases. This table didn't show anything, but you should know what is the number for the chlorine gas. Should be 0. Right, we just talk about why. Because chlorine gas either is a gas or chlorine liquid or chlorine solids. So obviously in the standard condition, we can only have a chlorine gas, right? And this is a diatomic. It's not a chlorine single atoms. So this guy is the most stable form for chlorine elements. So obviously this guy is 0. So that's why the enthalpy formation of the chlorine here is 0. Now, what are you gonna do? You're just try to figure out the difference between those two numbers. Then that's it. That's gonna be, then you can figure out what is the enthalpy of the reactions. 95.4 plus 2 times 92.3 negative. So this is how much for the reactant? A product. You subtract 74.6 negative plus 0. And the difference of that is the enthalpy of the reactions. The difference of the enthalpy of the reactions. So negative 205.4, negative 205.4 kilojoule per mole. Then that's gonna be the enthalpy of the reactions.
If they don't. Would it be 205.7? Okay, that would be 205, but we don't round up for safety.
Yeah, I'm not going to run this, otherwise that's too complicated. Okay, so that's gonna be the enthalpy of these reactions. Yeah, are you clear?
Yeah.
Okay,
Mm,
yeah.
right.
No, I'm just okay. Do you know the way? Now are you clear about the way to calculate?
It's not raining, but it's like
It's just a-
cloudy, you know?
It's a pro.
I'm okay. I just need more practice.
It's a product minus the reactant. It's just a product minus reactant.
Yeah,
Okay.
I don't know why it's difficult.
Stop overthinking it.
Okay, so then let's looking at the next one. We have these reactions and try to figure out enthalpy, standard enthalpy of these reactions. You see, they all has a circle on this. It's because the question, they give you a small circle, which means all of those numbers is happened in the standard condition. So you can only calculate the enthalpy of this standard reaction, standard enthalpy of these reactions. So now the enthalpy of these reactions, again, that's gonna be the product minus the reactant, right? So the product of the enthalpy formation, remember, this one is give you the enthalpy of formation. They have a delta H and it has an F over there. The F means formation. Okay, so each one has the energy associated with it. Then you just need to see, okay, how many we have? We have one of the H3PO4, that's phosphoric acid, and 5 of the HCl. So now we have phosphoric acid, negative. We have a negative 1284.4. That's phosphoric acid. We have one of this, and a plus. How many for HCl? We have 5 of them. Then your time, negative 167.1 kilojoule. And this add together will be just the sum of the enthalpy formation, and that is the product. Does make sense? Right? And then you subtract the sum of the enthalpy formation of the reactant. We have how many? We have a 1 PCl5 solids. You see PCl5 solids, then this giving is a negative 443.5. This is this. And then we have 4 of the water liquid. You see, now we can got the water liquid enthalpy formation of the water liquid, negative 285.8. So how many? We have 4. So 4 times negative 285.8. And the difference will be just the chemical reactions, the enthalpy of those chemical reactions. So let's figure out what is difference. 1284.4 plus 5 times 167.1. Okay, subtract 443.5 plus 4 times 285.8. Now you can get the difference. The difference is negative 533.2. Negative 533.2 and kilojoule and per mole. And this is gonna be exothermic reactions. So you see, that is the change of the reactions, enthalpy change of these reactions. Pretty straightforward, right? Yeah, just kind of what is the reactant, what is the product, what is the sum of the value for the enthalpy formation for the product, what is the sum of the enthalpy formation of the reactant, then that's it. Make sense, right?
Okay.
All right, so go ahead, work on the question number 3. And when you solve the problem, you need to be careful about the negative sign. Okay, the negative sign here help when you do the calculation. Okay, so now you can looking at here. So they already list everything over here. So 2 moles of this, 2 moles of the that's sodium bicarbonate. Okay, we have a we have the product minus reactant. So the product is negative 1130.9, and that is the sodium carbonate plus the water gas, and this is a water gas. You realize, you see, water liquid negative 285.8. Water gas, negative 241.8. You see, the enthalpy formation, that's gonna be different if you have the different phase, okay? Yeah, different state. Negative 241.8 kilojoule per mole, and plus the CO2, which is negative 393.5. So this is what we have for the reactant, and you subtract the product. We have a 2 of the sodium bicarbonate, which is negative 947.7. Okay, now let's figure out what is difference over here. 1130.9 plus 241.8 plus 3.5. So this is what we have for the reactant, for the product. You subtract 2 times 947.7, the negative sign. So the answer is 129.2. Okay.
Wait, why is it not negative?
Why? You put out a calculator, then that's not, then that's
I
100.
got the same thing, but it was negative.
You probably missed negative somewhere here.
I don't know. Suppose it's a positive number over here. So you need to double check the numbers that you put in there. Any people got the same number just like
Yeah,
me?
I got 129.2.
129.2, and that is a kilojoule per mole. Okay, and that is the enthalpy of these reactions. Okay, so today, yes, I'm talking about a pretty hard concept. That enthalpy formation is the hard concept. To be honest, when I first time learned this, I have no idea what my professor talked about. Okay, until later I realized, okay, how the enthalpy formation is formed. And even when I learned this, I even don't know why we need to got this number. What is the meaning of those numbers? I mean, is it necessary we need to have those numbers? I mean, it turns out it is necessary. Okay, yeah, because you see, enthalpy formation of those compounds can be involved in any kind of the chemical equations. As long as we know enthalpy formation of each of these compounds, and then we can just figure out what is the enthalpy of these reactions, right? But if we don't know any of this, if one of this we don't know enthalpy of formation, if we don't know enthalpy formation of this, and even we cannot figure out, okay, what is this reaction? Right? So enthalpy formation of those compounds is very important. And where to find those enthalpy formation of those compounds? It is come online, but the point is, what I mentioned over here, this is how this part is where the people find enthalpy formation of those compounds. They set up the equation. We're going to form one more of this, and the result during the experiment is the enthalpy formation. All right, so let's go to the